a little bit, but please excuse me if it doesn't look perfect. Unfortunately, we have to get used to this kind of thing. I think in the coming months, this will be what teaching will look like. That's how it seems right now to me. But anyway, thank you for inviting me. I really miss not be able to come. But yeah, I'll do my best. So my talk is, so we tested, hopefully you should see the board. The title is Rank Gradient in Profinite Groups. And the setup is gamma and G will all denote a group. And by G of G, I will just denote the minimal size of a generating set for G. And because a lot of the talk will be about P groups, GP will be the minimum number of generators of the pro-P completion of G, namely the dimension of the Frattini quotient of G modulo the P Frattini subgroup. And I want to give a bit of motivation to rank gradients in profinite groups, so I will talk a little bit about rank gradients of abstract groups as well. And that's why I have here defined the first Betti number of G, B1 of G. This is the torsion-free rank of the organization of G. Yeah. And the setup here is, as usual, we have a finely generated group, gamma, and then we focus on normal subgroups of gamma, and more particularly normal chains. So by normal chain, I mean a sequence of subgroups, gamma 1, gamma 2, each included in the previous one, and each normal and having finite index in gamma with trivial intersection. Yeah. Okay. Now, so the motivation is we're going to define the rank gradient of an abstract group. So first by gamma, I will denote an abstract group, and by G, I will denote a pro-P group, a profinite group. I think I should better stand this way. Yeah. So the rank gradient of G with respect to the chain gamma I, by definition, this is the limit as the index tends to infinity of the number of generators of each term of the sequence minus 1 divided by the index of the group gamma I. And the first observation is that this limit always exists because this sequence is this is a monotonic decreasing sequence. Yeah, and this is a nice observation which follows from the Schreier inequality, namely the number of generators of gamma I minus 1 is at most the number of generators of gamma minus 1 times the index. Yeah, this is the Nielsen-Schreier inequality. And we have equality for free groups. So if you apply this to each successive pair gamma I inside gamma I minus 1, you get that this is a decreasing sequence, so this limit exists. So this I first found in my own career. I found this in the work of Mark Lackenby. So Lackenby studied this in connection with three manifold groups. However, I learned later from Alex Lubotsky that in fact, in the context of profinite groups, this was actually studied much earlier by Lubotsky. And I'm going to mention this a bit later, in a moment later. So, and this was somewhere in the 80s. Okay, so why do we want to study this? There are a lot of parallels of this definition with the GRAW03 other invariants, namely the first Betti number. So if we replace this by if we replace this limit by beta 1 of gamma I, namely if you study the rank of the torsion of the torsion-free rank of each term of the sequence as normalized by the index, then a theorem of Luke says that if the original group gamma is finally presented, then this limit exists. This exists. And not only this is actually and equals the first L2 Betti number of G, which I'm going to denote beta 1 with that superscript 2. So this is the first L2 Betti number of gamma, which is the in short, this is the dimension of the first L2 cohomological group of gamma, and I don't want to define it here, but I mean, for the purpose of this talk, we can take this to be the definition of this limit, and in particular, this shows that the limit, if you accept that it's equal to some invariant which only depends on the group, it shows that this limit does not depend on the choice of the chain gamma I. It only depends on gamma. Yeah. And for Andre, and this is an open question. So this is an open question, which is: does this rank gradient with respect to the chain gamma I depend on the chain? And this is connected with questions about measurable group actions. So it turns out that this is connected with Gaboro fixed price question. Which asks us basically if every ergodic almost free measure preserving action on a probability space has fixed price, and price, the cost of the action is a certain ergodic invariant of a group. I'm not going to in this talk I'm not going to say anything about this question. I just want to just state it because it's still open. And I would really love to know the answer to this question. However, let me point out that for profinite groups, we can make the same definition now for profinite groups. Let's write it again. Now for G profinite, finely generated as usual, we can define, and then again GI open. Now this time they are open of and normal. In G, again with trio intersection. Then we can just define again rank gradient of G to be the limit of this the number of generators of GI minus 1 or the index. Now here I mean the topological generators. Namely the minimum size of a generating set for dense subgroup inside GI. Again, we have by the rank inequality. We do know that this is a monotonically decreasing sequence, just as before, so the limit will exist. But for profinite group, the beauty is that this does not depend on the choice of the sequence, because if you have another sequence. So basically, if HI is another such sequence, an easy compactness argument shows that the two sequences refine each other. What I mean by this is that given I, maybe I just write a bit higher on the port. So if hi is another sequence, so for all I exists a j such that gj is contained in hi, and conversely, for each j exists for each j exists I such that h is contained in gj, and therefore the two sequences will have the same limit. Yeah. And this is just a compactness argument. I mean, it's an exercise. So the nice thing is it's easy to define. This open question, this very hard open question, is completely irrelevant in the world of profinite groups. You really know that this limit is some invariant of the profinite group itself. There's no choices to take. So it makes sense to study it. And by contrast with the abstract group situation, not much work has been done for profinite groups, and the purpose of my talk today is to just focus on a couple of open questions that are connected with this, and I'm going to talk about them in a moment. But before, let's give some examples of groups which have positive rank gradient. I mean, most of the time, if you see this for the first time, then you may ask, what is the rank gradient of your favorite group? And the chances are that the answer will be 0. Yeah. So most groups that we are familiar with have rank gradient 0. For example, every solvable group has rank gradient 0. Every amenable group has rank gradient 0. SLN Z, so the rank gradient. So if gamma is solvable or more generally amenable, or more generally also or higher rank, non-uniform, that is in a semi-simple Lie group. For example, SLNZ for n at least 2, n at least 3. Then the rank gradient of gamma is 0 with respect to any chain. So this, I'm combining results by several people, so I don't have time to quote them, so I apologize. By contrast, the only obvious examples of groups with positive rank gradient, of course, will be free groups, right? So for free groups, we have equality, and in the Nielsen-Schreier inequality, we have equality, and therefore we automatically get that. So if gamma is the free group on D generators, then the rank gradient of gamma with respect to any chain again will be G minus 1. Yeah, because the number of generators minus 1 is multiplicative. And other examples, surface groups. Surface groups which are of course not abelian, not z squared, have positive. Gradient, and we can try to quantify this by trying to guess that somehow groups with positive rank gradient should be big in some sense. But in what sense? Yeah, they should be big, but in what precisely sense? So usually when people think about big groups, they either think that they contain free groups or they map onto free groups. However, for abstract groups, this turns out to be not the case. So it turns out that there exist torsion of groups with positive rank gradient. So mention. So exist. So this is a result by Dennis Olsen, which says exist torsion residually finite. All my groups are always residually finite, but let's just emphasize it. Exist torsion residually finite groups with positive rank gradient. Okay. So this means that they cannot be large in any. I mean, they neither contain free groups, nor neither do they map onto free groups. This also was reproved by Jan-Christoph Schrager-Puchter, and I'm going to talk a little bit about his proof in a moment because it's very useful in the context of propi groups. So we don't have this characterization, but still we don't have any kind of connection with free groups automatically, but these groups are not finally presented, yeah? And if you add finite presentation to it, to the group, then there are results which say that the groups are some large. That the groups are large in some sense. So here I should mention the result by Lackenby, which shows that if gamma is a residually p group, with positive beta to beta number, in fact, I can replace, in his proof, he only uses the fact that the mod p gang, so that in fact, just need that dp of gamma I grows linearly, so that basically over gamma I, this limit is positive, where gamma I is the Frattini series. Every time you take the Frattini, the p Frattini, so you fix a prime. Yeah, this p is a prime, and you take gamma I to be the I term of the Frattini series, and then if you know that the mod p number of generators, dp of gamma I grows linearly, which follows from the fact that the L2 beta number grows linearly, is positive, then gamma is large. More precisely, some gamma I maps onto a free group, maps onto F2. Yeah, so the group virtually maps onto a free group. I forgot something very important, that gamma is finely presented. Finely presented. Okay. So if your group is finely presented, and if you can approximate it with finite p groups, and it has positive gradient with respect to these groups, in this sense, then it's large. Yeah. So this kind of crazy examples of Olsen and Puchter don't exist for finitely presented groups. And Dennis Olsen has this nice question about trying to put some properties on abstract groups which are finitely presented and with positive L2 beta number. So he proved, Dennis Olsen has this conjecture that all finitely presented residually finite groups gamma with positive L2 beta number are cylindrically hyperbolic. So a cylindrical hyperbolic is a generalization of hyperbolicity. And again, in some sense, it says the groups are large, right? So they contain free groups and so on. Notice that positive L2 number implies positive rank gradient, right? So the rank gradient is a upper bound for the L2 number, because the number of generators is an upper bound for the rank of the organizations. So this conjecture is not so far-fetched as it might seem, because it's a theorem of Olsen that this conjecture is true if gamma maps onto the integers. So if the organization of gamma is infinite, then this is true. Yeah, it's a nice short proof using combinatorial group theory. So we do have some kind of grip on the finitely presented groups of positive rank gradient. Yeah? Maybe not a complete picture, but we have something that we are aiming for. Okay. So what about profinite groups, right? So here is when my talk really starts. Okay. Well, let's go back to basics. So, what are the examples of groups with positive rank gradient? Well, we can start with the free profinite group. So, if G is Fg hat, the profinite completion of the free group on D generators, then again, because the rank gradient of G is G minus 1, so if G is more than 1, then we have an example of a group of positive rank gradient. Now, sticking with free groups, this can in the abstract case, we can characterize groups for which the rank gradient is exactly constant at all times. So, so if in this case, when G is the free group, so certainly we have in that case that if H is an open subgroup, not even normal, then the number of generators of H minus 1 is multiplicative. It's exactly d of G minus 1. Yeah? If any open subgroup of G, then H is a free group of precisely this rank plus 1. Yeah? Because you can always intersect with the dense free profinite group with the dense FG inside, and then use the Nielsen-Schreier theorem for abstract free groups. So we have this equality for free when G is a free group. And we can ask, does this characterize free groups? So does this characterize free groups? Okay. Now, what is the situation in the world of abstract groups? For abstract groups, the answer is yes. If gamma is an abstract group, and so what do we need? We need a residually finite, and if the number for all H subgroup of finite index in gamma, the number of generators of H minus 1 is multiplicative is the number of generators of gamma minus 1 times the index, then gamma is free. Yeah. So this is this problem has a nice history. It was actually asked by Lubotsky and Van den Dries. So this fact was not known to them, and it was asked by them. And the reason they asked it is because they solved the corresponding problem for profinite groups. First, so it turns out that if gamma is a pro-p group, so if G is a pro-p group, okay, now I can erase this very finite. And for all open subgroup of G, the number of generators is multiplicative. Then G is a free pro-p group. Okay, so this is the result by Lubotsky and Van den Dries. And the proof is not hard. I mean, this is an old paper from the 1980s, I think. But by modern standards, the proof is not hard. I mean, it's like a like final year undergraduate students who is studying profinite pro-p groups should be able to answer it. In fact, it's easier than the result for abstract groups. The reason being that the number of generators for pro-p group is a nicer invariant. It's easier. It's easier to work with because it's the dimension of certain vector space. So they asked this. So Lubotsky and Van den Dries answered it for pro-p groups first, and then they observed that this is false for profinite groups. So again, now if G is a profinite group, and suppose again for all open subgroup of G, the number of generators minus 1 is multiplicative in the index, then G may not be a free profinite group. And here's an open question: can one describe profinite groups with this property? Let's call that a group has. I don't want to call this a Nielsen-Schreier property because there is a Schreier property which is say something different for groups. Let's say that we say that G has the multiplicativity for rank minus 1. So let's say this is the rank minus 1 multiplicativity property. This is it. So every subgroup of finite index of any open subgroup has rank which is exactly as if the formula is exactly as if the group is free. Then what can you say about the group? So this question has connection with some Galois theory. So this is connected with some Galois fields. So this is connected with some Henselian fields. And Galois theory. I admit I don't know very much about it, if you want to learn more about it, you should look up the papers of Mark Schusterman. So he has one or two papers that study profinite groups with this property. In particular, I think he characterizes the pro-solvable or maybe the super-solvable groups with these properties. So I'm not quite sure. But Mark Schusterman is the man for you. But I can give an example of how far the group is from a free group. You may think, okay, the group may not be a free group because maybe maybe a closed subgroup of a free profinite group, and that doesn't have to be free. But even this is not true. It's possible that the group G does not have finite cosmological dimension at all. Yeah. So let me just give a quick indication how one can construct of such example. Let me just look at the time. Okay, I'll do that. So we start with a sequence of primes. We choose a sequence of primes, P1, P2, and make them distinct. So use a sequence, infinite sequence of primes. Okay, and then we start with F2, the free group on. So this is my gamma is the free group on two generators. And then I define inductively a sequence which such that gamma 0 is gamma. And then for the next term of the sequence, gamma I plus 1, I'm going to take the ith term of the ith prime, and I'm going to take the Frattini subgroup of the previous group, but for the prime pi. So this will be gamma I derived times gamma I to the pi. Yeah. So this is the pi Frattini. Subgroup of gamma I. Okay, so each of them is a characteristic subgroup of finite index, and then you see that okay, and then what is my group G? G will be the inverse limit of these gamma modulo gamma i's. Yeah. Inverse limit. So each quotient is a finite group. And because you see that the rank of so if you see that the number of generators of gamma I modulo gamma I plus 1 right. The number of generators of gamma I modulo gamma I plus 1 is precisely the size of this Frattini quotient, but this gamma I is a subgroup of the free group F2, so this is exactly the same as the number of generators of gamma I. I mean, this is basically the Frattini quotient of this group, which has the same number of generators, and this satisfies the inequality, right? This satisfies this is equal to G of gamma minus 1 times the index. You immediately see that if I put Gi to be the closure of gamma I inside G, then the number of generators is exactly the number of generators of gamma I, because Gi maps onto gamma I modulo gamma I plus 1, and the index is the same, right? And the index of gamma I G is the same as the index of Gi. And so these GIs will have will satisfy the multiplicativity of the rank minus 1. But the moment you have one chain that satisfies the multiplicativity minus 1 property, it's true for all subgroups. So this is again an easy exercise from the multiplicativity, from the monotonicity of the rank gradient -1. Yeah. So just using this obvious fact, you get very easily that G is a group which has the multiplicativity property for rank -1, but now G is not free because in fact the zero subgroups of G, you can see, because we're involving different primes, the size of this group I mean, the group is basically an extension of elementary abelian groups for different primes. So what I want to say is here that all zero subgroups of the profinite group G are finite. Namely, the pi zero subgroup is precisely the size of this quotient and nothing else, because all the other factors involved in these solvable groups are just different primes. So this is a pro-solvable group. Yeah, I should point out this is a pro-solvable group. It's an inverse limit of these solvable groups. But that all the zero subgroups are finite. So this means that, for example, the group is not projective. It doesn't have finite cohomological dimension. It has a dense, locally finite subgroup. I mean, sorry, what was I saying? It's not virtually torsion free even, yeah, because it has torsion of arbitrary large size. Okay. So even for this even for this simple question, for profinite groups turn out to be quite surprising and involved and not without a clear answer yet, at least to my knowledge. So we have to be a bit careful when we approach profinite, the rank gradient of profinite groups. We may hit something a bit deeper than even the abstract group case. Having said that, what else can we say? I mean, here's a very natural conjecture that I'm willing to write down, because to the best of my knowledge, nobody has actually put it down in words. It's the following. So let G be a profinite group with positive rank gradient. So rank gradient of G positive. This is a conjecture. Then G has a dense field subgroup, has a non-abelian dense free subgroup. Okay. So it's large, at least in that aspect. In particular, G does not satisfy an identity. Yeah? So in particular, a group identity. Yeah? Okay. It's a very simple conjecture to make, very, very natural also, I think. Now, I have to say that this is open to the best of my knowledge. Even the fact that G does not satisfy a group identity is an open. I'm not aware of any result which gives it. And if it's not, I can sketch a. So maybe I'll just say, okay, let's call it a theorem. It is really just an observation that puts together several deep results. Is that the conjecture is true for propy groups. So if G is a propy group with positive rank gradient, then indeed G does not satisfy. No, sorry, contains a dense free subgroup. Okay. I want to mention this interplay with this connection to identities leads me to a bit off track, but let me just mention it that for abstract groups this is an open question. Here's the open question. I learned this from Andreas Tom, so he is very interested in this question. So I just write the question by Andreas Tom. Let G be a residually finite group which satisfies an identity. Finitely generated. Must G be amenable? So there is no counterexample known that a residually finite group which is satisfies an identity and it's not amenable. Yeah. So this is not quite the same. I mean, it's not a direct parallel to identities in profinite groups because all profinite groups are compact and so amenable. But one can ask it, for example, for the dense subgroups inside a profinite group, right? I mean, certainly in a propy group, you can take a okay, so this is just a side question, which is quite interesting, I think. All right. So let's return to this, yeah, and see how does it follow. Okay. So this there's a parallel here with GRAW03 groups, right? So in GRAW03 groups, this is a well-known theorem. So let me just write again a known theorem. If G is a propy group which is the GRAW03, then indeed G contains a dense free subgroup, and this is a theorem due to Wilson and Zelmanov. Okay. And there are strong connections between GRAW03 groups and groups, propy groups of positive rank gradient. So here is a little observation. Observation is that if G is a finitely presented GRAW03 groups, finitely presented group of positive rank gradient, propy group. With then G is virtually GRAW03. Okay. And this is indeed an observation because if you have a finitely presented group, and suppose that G is presented by a finite set of generators and a finite set of relations as a propy group, then if you take a subgroup here, which is an open subgroup, then this one will be presented by a finite, again will be finitely presented by a set of generators x1 and relations r1, such that basically h1 will grow linearly in x and r1 will grow linearly in r. So that basically h1 grows linearly sorry, in the index, in the index is also R1 grows linearly in the index. Yeah, if you take the Nielsen-Schreier way to rewrite a presentation, you get the number of relations also grows linearly with the index as number of generators. But then if both quantities grow linearly, then eventually this R1 becomes less than the number of generators squared over 4. But then, okay, you have to be careful because this x1 is not necessarily so x1 may not be equal to the number of generators of H as a pro-P group. Yeah, because there could be a lot of redundancy here. But this is where you use this condition, and then you certainly get that this finite presentation for open subgroup will satisfy the Gauch-Farevich inequality, and so the group will be Gauch-Farevich. And then you can invoke this theorem and immediately say that if G is a finitely presented pro-P group of positive rank gradient, then G contains a free subgroup which is dense in some open subgroup, which is good enough for many purposes. So we are almost there just with Wilson and Zelmanov theorem, but for finitely presented groups. So this does not work if G is not finitely presented. So to prove the result in full generality, I mean, I tried a lot of things first. You can get quite far with elementary methods. For example, a completely elementary, you can prove that if G is pro-P with rank gradient of G positive, then G does not satisfy an identity. For this, you need nothing. I mean, this does not need any deep theory. It's just follows from the kind of the properties of finite index subgroups and the fact that the rank gradient was positive. Okay, but to have a dense free subgroup, what you need is that G does not satisfy a coset identity, right? So this is so let me see. Let me just write this. An easy proposition is that a profinite group, okay, let's say a pro-P group, has free subgroup non-Abelian. If and only if dense if and only if G does not satisfy a coset identity. So a coset identity is a non-trivial group word which is satisfied on the set of cosets of some open subgroups on G. Yeah. Right. So this is what we have to prove. And actually, this is true for any even for profiling. So it's just complete general result. Yeah? And here's the methods that Wilson and Zelmanov come in play, because how they prove this result? Well, they use the same thing, that if G does not contain a dense free subgroup, then G satisfies a coset identity, and they proved that if G satisfies a coset identity, then the associated V algebra of G satisfies an identity. So this is another result. So if G satisfies a coset identity, And let's call this for any abstract group. So if gamma satisfies a coset identity for finite index coset, for cosets of a finite index subgroup, then LP gamma satisfies a Lie algebra identity. Okay, what is LP gamma? This is the Lie algebra of defined by the quotients by the dimension subgroups. So we have people who work in tropy groups use this quite a lot. The associated Lie algebra is when you take the dimension subgroup filtration, also called the Zassenhaus filtration of gamma, and then you factor out the successive layers, and then this becomes a Lie algebra. Wilson and Zelmanov in a note proved that, well, six pages, proved that if a group satisfies a coset identity, then its associated Lie algebra also satisfies an identity, but for Lie algebras. And now Zelmanov's techniques for solving the solution of the Burnside problem come in play, because Zelmanov proved that a finitely generated residually finite torsion group, residually p torsion group, which associated Lie algebra satisfies an identity, must be finite. Okay. So another theorem of this is Zelmanov. If gamma is residually p, torsion, finitely generated, and its associated Lie algebra satisfies an identity, then gamma is finite, is a finite p. Okay, this is part of his solution of. In fact, this is the solution of the Burnside problem for p groups, the restricted Burnside problem. Okay. So, and then how does the proof goes of the profinite of the theorem that I just wiped out here? Well, we start with the Goldschiffer-Average group. We take a dense subgroup inside. Now this we call it gamma. Now, and if the group satisfies the coset identity, then gamma satisfies the coset identity. So it is finitely generated. It is residually finite. It satisfies an identity. So the Lie algebra satisfies an identity. The only thing missing is that the group is it torsion or not. But okay, if it's not torsion, then what you do by the well-known trick for Goldschiffer-Average groups, you just throw in the relations which are high powers of all the group elements in gamma, and the group still stays Goldschiffer-Average. So you end up with a torsion and infinite group here, and that contradicts the Zelmanov's theorem. Therefore, your pro-p groups, your Goldschiffer-Average pro-p group cannot satisfy coset identity, and therefore contains an open, contains a free subgroup. And this is indeed the same setup that works for rank gradients. Okay, the required. Oh yeah, I'm almost out of time. So the required trick is a result of Puchta. So I should quote here Jan-Christoph Schnage Puchta. Who proved essentially the following result, that if okay, so he didn't prove exactly the same thing, but his methods can be used to prove the following result. So if gamma is a residually p group with a positive mod P gradient. So let me just write RGP of gamma positive. Then gamma has a torsion quotient, gamma bar, with the same property. Such that the mod P gradient of gamma bar is positive. He applied basically his theorem, the way it's written in his paper, is for free groups, but actually it applies to any finitely generated resolute P group. So if you just follow his proof, you get this. And now if you combine the same method with the Wilson and Zermanov techniques with the coset identities, you immediately deduce that you deduce a theorem that just if G is a profi group with positive rank gradient, then G has a dense free subgroup. So yeah, it's kind of pretty easy using these results. What I would really like to know is how can one prove this for profinite groups in general? I'm very confident that it is true for profinite groups as well. But unfortunately, these methods don't help at all for profinite groups, because the number of generators then becomes very mysterious, and you cannot approach it with Lie algebra methods. And yeah, thank you very much. Awesome, yeah? Yes. Fine. Yes. The final presentation is also needed because otherwise you do have these torsion examples that he constructed and Puchta as well. Yeah. Yeah. I think for residual fineness also they count examples because they exist. They exist. Oh, wait a second. I was about to say they exist simple finitely presented groups with positive L2 Betty number, and I'm not sure that implies that they are not numerically hyperbolic. I'm not sure about that. I would go and look at his original short paper. It's in the bulletin of the LMS. He may probably have some discussion about it. Oh yes, the ones that are not virtually metabelian. Oh wait. No. The any two generator. So the L2 Betty numbers of one related groups are known, and they're exactly as you would expect. They are basically, instead of D-1, where D is the number of generators, it is D-2. So it is 0. So yeah, so all bounds like a group have 0 L2 Betty number. Also proves it already from his result. It shows that any group of deficiency more than 2 is acylindrically hyperbolic. So probably, you need to look at something with deficiency 0 or deficiency 1. Thank you.